So the newest way that I'm going to approach theory development is through gyrochronology. I have a new paper here. Now, before we even begin, we have to learn how to spot the assumptions that establishment has made concerning gyrochronology. And gyrochronology is basically you have a star spinning, and depending on how fast it's spinning, you can determine how old the object is. It's pretty straightforward. Um, Being that the dogma doesn't understand how evolved stars get and what actual old stars look like, they're kind of grasping for straws when it comes to saying, well, we can determine how old a star is by how fast it spins, because they don't know what the oldest stars even look like. And that's very problematic. And if you go on Wikipedia and look up gyrochronology, it's essentially a field that's really only about 16 years old. I'll read this out to you guys. Gyrochronology is a method for estimating the age of a low-mass star like the Sun from its rotation period. And there's a problem with that. Estimating the age of a low-mass star like the Sun. The Sun is not a low-mass star. The Sun is a very massive star. It is 330,000 times as massive as the Earth. And those that understand that the Earth is 6 sextillion tons of rock, water, atmosphere, and metal. To say the Sun is a low mass star is like it doesn't make any sense. I don't know why astronomers have been allowed to get away with this, because they're completely wrong. The term is derived from the Greek word gyros, chronos, and logos, roughly translated as rotation, age, and study, respectively. It was coined in 2003 by Sidney Barnes to describe the associated procedure for deriving stellar ages, and developed extensively in empirical form in 2007. One should wonder, what exactly was being designed? How were they determining how old these stars were back in 2007, when essentially zero literature exists stating that stars evolved greatly into their iron, nickel cored, mantle layered remains, which resemble what they call planets? What exactly were they figuring? From my end, the discovery was made in 2011. From Anthony Abruzzo's end, he wrote it down, and I think the earliest paper I saw was 2008. Of course, he had the idea even before that, but didn't write it down. So back in 2007, back when I exited the Marine Corps, there was no empirical form for gyrochronology anyways. Let's see. There are lots of things to gather from gyrochronology. Now, the Sun, its rotation at the poles is 36 days. It takes 36 days for the pole to rotate. And towards the equator, the Sun rotates at about 24 days. So the equator spins faster than the poles. And I drew a little diagram here. But the velocity is really fast. The surface of it is spinning extremely fast because it's a freaking giant object. The Sun is giant. If you take the Earth and line it up, Earth to Earth to Earth to Earth, the Sun is about 110 diameters of the Earth. That's a big star. And to see that the difference between the rotation rate of the poles differs by about 150% is phenomenal. That's crazy. That's what we should expect to see on very young hot stars, is a differential rotation by those huge amounts. And I wrote that in the paper. As the star cools and collapses, though, what happens is the differential rotation between the poles and the equator slows down significantly. The differential rotation for Jupiter, I have this in the paper, is 9 hours and 56 minutes for each pole. And in the equator, it's 9 hours and 50 minutes, meaning the difference in rotational rates, it collapses into almost being indistinguishable. But as we know, if there's differential rotation and the object is gaseous, well, that's why it can have its differential rotation to begin with. There's no solid surface, really. And as the star continues collapsing, that differential rotation in the outer regions will slow down considerably because the crust starts forming. The material gets more viscous. It becomes more like honey and like magma. You know, have you seen videos of magma flowing? It's like honey. Oh, it's super hot honey. I wouldn't want to touch it or be near. I mean, I would like to see lava one day, but think about the interior like that. When you have a very viscous interior, the differential rotation is going to decrease significantly until that honey or that lava or magma solidifies and creates a crust, until eventually a very old star will have no differential rotation because the crust will have formed. The Earth doesn't have any differential rotation between the poles and the equator. It's 24 hours up here, 24 hours in the middle, 24 hours at the bottom. Of course, it's like actually about 23 hours and then 50 something minutes, something like that. It's not exactly 24 hours. But they're all the same, and that's the big point. As well, I have yet to work on the spin rates for these objects, how fast the velocity is, and how fast they're spinning, because a lot changes when the object loses mass. It can decrease its spin rate by ejecting mass away from the star, just like a figure skater extends her arms out to slow down and she pulls her arms in to speed up. We can use that basic principle to determine how fast the mass is lost on a star as it cools and evolves. For instance, if you have, say, like a red dwarf and it's shrinking and not losing mass very fast, if it's shrinking its diameter, not losing mass very fast, it's going to start speeding up. So the rotation rate will go maybe from like a regular day, down to like half a day, and it'll start spinning really, really fast. And I wrote that in there as well. And being that it's collapsing on itself, there might be another reason as to why it starts flaring, because it's trying to get rid of that material as much as it can, so it can collapse. And it won't have to keep on spinning faster and faster. It can eject the material out, so it can continue collapsing and moving into brown dwarf stage of evolution. As well, the oldest dead stars in our system, two examples, Mercury and Venus, their rotation rates are so slow that on Venus, I calculated this, you can literally walk on the surface. Well, you can't walk on the surface because it's too hot, it's not 900 degrees. But if you could literally walk like maybe, I think it was like 3.5 or 4 miles an hour. I think that translates to what, 7 kilometers an hour. But anyways, you can walk and you can watch the sunrise as the object is rotating, and you can watch a perpetual sunrise on the surface of Venus if you could walk on the surface, which you can't. But the Earth, you can't do that, because the Earth at the equator, I believe, is spinning around 1,000 miles an hour or 1,100 miles an hour. You'd have to be in a jet to watch a perpetual sunrise or a perpetual sunset. Mercury's day, where it spins once around, is 58 of our regular days. And Venus's day is 243. That rotation rate is so freakishly slow, it basically means that they're dead. We should expect to see rotation rates of the dead stars in the exoplanetary systems to be very, very slow, like Venus and Mercury. Stars that have that are more alive, I say alive, but I really mean like fluid motion and gaseous material, and they're really, really big, and they have, activity in large magnetic fields, and they're just happening, they're active. Those objects can still have the leftover rotation from earlier stages of evolution, which means genuine gyrochronology means we can actually date how old stars are by how fast they spin, referencing other stars that are near the same stage of evolution. It kind of goes haywire when the star ages, because there are a lot of different factors involved when the star is orbiting, and it can experience tidal forces really close to a host, and it can show one face and then get ejected out, and then basically get spun up again. And there's a lot of other variables in here, but I just wanted to set the record straight that a low mass star isn't the sun. A low mass star is something like the Earth. As well, gyrochronology can be applied to every single large celestial object, essentially, that was a complete star at one point. It can be applied to all of them. So when establishment, they delineate between, oh, this is a star because it's bright and hot and shining, and this isn't because it's mostly gaseous. They're completely wrong. They're completely wrong. They have no idea what they're talking about. A young star is like the sun, and as they cool, age, and evolve, their spin rates change, and they move into the classification of planet, but really they're just older stars, and we can take gyrochronology and figure out how old they are by how fast they're spinning and what's been happening to the whole body throughout its history. All right, you guys, today is June 11th, 2019.